Hello, good morning. I am representing the three-dimensional imaging and display laboratory at the University of Valencia. This laboratory, this group, is co-head by myself and Professor Genaro Saavedra, who is also here in the room. We belong to the Faculty of Physics of the university, so in some way we are a little bit exotic in this engineering atmosphere. This is our group in a, not very hard-working moment. Our group is mainly also composed by physicists, and we have been, for the last many years, we have been working in 3D imaging and display of microscopic and macroscopic objects. Concerning microscopy, we have been working in confocal microscopy, structural illumination microscopy, digital holographic microscopy. I will not speak about that. I will concentrate my talk in the in the topics which are related to this training network. So in this sense, the first topic I'm going to face is how to apply this very old Lippman concept to the application of microscopy. You know that the original idea of Lippmann was obtaining many different perspectives of the same scene by use of a microlens array. So what we make here is that we try to implement this in a microscope. This technique, in fact, maybe by many of all of you is known as light field microscopy. In fact, I prefer to use the word integral microscopy because in order to recognize Lippmann contribution to this topic, and how can we build an integral microscope? So it's very easy. In fact, it's like a plenoptic camera, but with a big difference. So there is a telecentric arrangement, telecentric coupling between the objective and the tube length. And then, in this sense, the relation between the microlens array and the aperture stop is a transposing relation, in the sense that the one is in the front focal plane of the tube length, the other is in the back focal plane. In this sense, for example, with this integral microscope, working with very small samples, what we obtain is a collection of usually many micro images, and in any micro image, behind of any of them, we have a small number of pixels. So this is the this is the presentation of the radiance map, of the plenoptic map, and what we can, the most important issue here is that by simply performing a transposition of this matrix, of this function, we can obtain the perspective views, what we can call the elemental images. So by simply transposing of this function, or by simply taking the rows in this function, we can obtain different views. Then in this case, we have only few views with many pixels each. And it is, from my point of view, it is easier to work with this second way of having the information. And then from these orthographic views, it is easy to render the depth images, or calculating depth maps, or So it's working. Okay. So this is an experiment we did similar to the experiment performed by Levoy some years ago. Then we have a fluorescence sample, and then we obtain it in the left, the collection of micro images, many micro images with a few pixels each, And then from them, it is very easy. We make the transposition. So the right hand video is directly, a video of the transposition images, and we can render the depth images from them, which is the main problem of plenoptic technology, integral imaging technology. Main problem is that we lose resolution. Losing resolution is a big problem always, but in microscopy is a key problem. So, in fact, if you lose resolution, this cannot work. So if you are implementing a technique in microscopy which is losing resolution, nobody will accept that. So then we recently, this is an example, for example, top left is a direct image of a new SAF test. Top right is the plenoptic image. Here are the views obtained directly by transposition of the plenoptic image, and bottom right is the reconstruction. You can see that reconstructed image has poor resolution. So if you build a microscope with poor resolution, then this is not a microscope. This is an imaging system. So then our proposal was simple, but I think effective. We propose to increase the increasing of the resolution by physical interpolation. Physical interpolation, it means that, I don't know if it can work one more time. Okay. Physical interpolation means that if you insert a parallel plate in the path of the light, and you make this parallel plate oscillate that way very fast, you can obtain two plenoptic images shifted by half the pitch of the microlens. Then you can obtain a plenoptic map which is twice denser than the previous. And in this way you can multiply by 2 the resolution of the system. So, okay, this is an example. We have codified in different colors 2 different views, and then in the right-hand side is the example of how to interlace these views. And here is some examples on refocusing in different places, and in which we show, if we compare with the previous one, that the resolution has increased significantly. So we are still far from the resolution that people from microscopy want, but we are in the way. And maybe here, I don't know if they work, yeah, some views. So in the left-hand side, we can see, images of biological samples. Images in the left-hand side, we have images obtained with the integral microscope. And in the right-hand side, we can see the images obtained by using the physical interpolation. So we obtain double resolution. This is good. I think this is still is not acceptable by people from microscopy. Then our next idea is to try to implement a different way of capturing the radiance map. Our idea is the following. Then our plan is to remove the microlens array and then to make a windowing in the aperture plane of the microscope. In this way, for example, if we make this window in the aperture stop, we can use all the resolution of the sensor. And then in this way, we are capturing only one row, but with much higher resolution. So this is a conventional integral microscope, and this is the windowing, the aperture stop. I think I have here a movie. So if we implement some kind of dynamic system for windowing the aperture stop of the microscope, for example, that way, then we will be able to obtain many, let's say, orthographic views of the sample with very high spatial resolution. Then the combination of them, I'm sure we still don't have results of this, but the combination of this, I think, will provide finally integral microscopy images with a good resolution, with capacity of generating views, and with capacity of making this depth rendering. So in fact, one of the ESR that is coming in to our lab will be developing this system. So another of our proposals is related with making different, maybe novel ways of performing the depth rendering. So, and then here we take profit from something that is very simple and that is evident. Is that, for example, if we have an object, the red one, which is for a given distance from our collection of camera, then we find that this object provides some, copy of each at different distances. So we can define a point spread function for associated to any depth distance. In this way, for example, if we have two objects, the red and the blue ones, we find that they provide copies in the detector, but with different distance between them. The parallax is different. The disparity is different. Then in this way, for example, from a collection of elemental images, we can select 3 by 3 of them, and we can apply a deconvolution algorithm, and depending on the period of the periodic, let's say, point spread function, we reconstruct in one plane or different plane. So you can see that we don't make reconstruction plus deconvolution. We make simply deconvolution. The deconvolution directly provides the depth rendering. So our idea is to go further, and this will be another of the topic related with this network. Our idea is to go further and substitute this, let's say, point-like point spread function by periodic point spread function that take into account the diffraction effect. In this way, I think we will be able to obtain much better results. Anyway, this technique is able to, allow some extra digital processing. For example, top left, we can reconstruct simultaneously in two different planes. For example, the plane of teacher and the plane of Albert, and are simultaneously. Or, for example, we can make an all-in-focus image in bottom right. And to finish, I would like to speak about a technique which is somehow related with things we have seen here this morning, maybe the talk by Silly from Fraunhofer Institute. We want to make also some processing from, let's say, the collection of elemental images obtained with an array of camera. So our proposal is the following. We can make refocus, we can change the viewing angle, we can change the center of the field of view, but for that we don't need to calculate disparity map, we don't need to calculate depth map. Our proposal is, okay, I would say simple. We simply propose to fix windows in the collection of elemental images, and we need to fix the window size and the window's position here. And fixing these two parameters, we can select at will fixing this parameter and cropping these images, we can fix at will many parameters of the display. So then we can, we can make something like this. So if we can shift the window center, or we can make the window bigger and smaller. And okay, so these are examples. So from this collection of elemental images, by simply changing this parameter, we can calculate, for example, this, in which top left is the collection of micro images calculated from the elemental images that are projected here in the monitor. So this is an iPad in which we put a microlens array. For example, in this case, our decision was, the viewing angle. But for example, in the right, we decided to enlarge the viewing angle, so to go closer to the scene. And in this case, we decided to change. This is providing real 3D. So in fact, if you are here, you can touch. So here we decided that the cook here is in the plane of the microlenses, but here, in the plane of the microlenses was the window, and the cook was outside. So we can decide all of this, and for this decision, we simply need to, to crop and transpose the plenoptic information. I think I have only two more. And we also can make movies. So from, Lego is always present here. From the same collection of elemental images, we can calculate all of this by simply moving the window by which we crop the elemental images. And then, of course, we can project this in our integral imaging monitor. So we have a movie which has a full parallax, and then we decide which part of the scene is, behind the monitor, which part is in front of the monitor, which is in focus, which is out of focus, from a single collection of elemental images. And to finish, okay, let me say a few things about our laboratory or our university. So University of Valencia is a medieval university. It was founded more than 500 years ago. Within this university, Faculty of Physics, I would like to remark that we are ranked among the top 100 universities in the world in physics. Yeah, in fact, our faculty is very famous in Spain, so we receive students from everywhere in Spain because of this, because we are famous. So there is also a rank in Spain, and we are in the #1 in Spain from Spanish point of view. And the PhD program in which these candidates will be enrolled has been recognized by our Ministry of Education with the Excellence Mention. Concerning our group, in the past 7 years, 5 of our students have finished their PhD thesis, 2 of them obtaining the best thesis award in physics. At the moment, 5 students are still working in their thesis project in our lab. We hope in the next few months we will have 7. And in the last 10 years we have published about, in average, 6-7 papers per year in high-ranked journals. Okay, that's all. Thank you very much.